Welcome to The Explainer, where today we're going to pull back the curtain on the delicious science behind one of the fluffiest treats on the planet.
I mean, it really does feel like a magic trick, right? But it's not magic. It's actually this incredible balancing act between chemistry and physics.
And get this, it all starts with a plant. Yep, that's right. Way before they became a campfire staple, marshmallows actually came from the sap of a plant. All right, so here's how we're going to break it all down. First, we'll look at where these things actually came from. It's not a factory. Then we'll get into the marshmallow formula itself. After that, the secret science of the syrup, how to whip it up into a cloud, and of course, what to do when good mallows go bad.
Okay, first up, not from a factory. Let's dig into how this whole thing got started, way before factories were even a thing.
Man, the marshmallow has had quite a journey. It all began back in ancient Egypt, believe it or not, as a medicine made from the sap of the Althea officinalis plant. That's where the name comes from, marshmallow. But the big game changer happened in the 1800s when some clever French confectioners decided to swap out that plant sap for gelatin. And boom, the modern marshmallow was born.
All right, Section 2, the marshmallow formula. So what actually goes into making that one-of-a-kind fluffy texture? It all boils down to just three main ingredients, the three pillars of fluff.
Okay, so think of it this way. At its core, a marshmallow is just a simple structure. You've got gelatin, that's your architect, building the whole framework. Then there's sugar, which does two jobs. It's the sweetener, obviously, but it also gives the foam its shape. And finally, you have water, the medium that dissolves everything and gets the party started.
And the absolute key to making this whole thing work is a process called gelation. Basically, when you mix that hot syrup with gelatin, the gelatin molecules unwind and then link up as they cool, forming this incredible three-dimensional net. It's like a microscopic spiderweb. And that net is what's going to trap all the air we're about to whip into it, giving you that perfect chewy texture.
All right, moving on. But listen, creating that perfect gelatin net, it all hinges on getting the sugar syrup just right. And I mean just right. This is probably the most critical make-or-break step in the entire process.
Okay, 240 degrees Fahrenheit. This is the magic number. You have to hit this exact temperature. No more, no less. In the candy world, they call this the softball stage, and it's the sweet spot for creating a structure that's firm but still perfectly pillowy. So why is that temperature so important? Well, it's all about water content. By heating it to 240 degrees, you've boiled off just enough water so that the sugar concentration is between 85 and 87%. That's the perfect concentration to cool down into a firm, bendy candy instead of, a sticky mess or a hard rock. But there's a problem. Sugar wants to turn back into crystals. It wants to get gritty. So to stop that from happening, we add something called an invert sugar, things like corn syrup or honey. Think of it like a bouncer at a club. The sugar molecules are all trying to line up and form a crystal, but the invert sugar molecules get in the way, blocking them, keeping the final texture perfectly smooth.
And what's really cool is seeing how this science plays out with modern sugar substitutes, like in keto recipes. Xylitol works great, makes it denser, chewy marshmallow. Allulose, also awesome, gives you a super fluffy one. But erythritol? No way. It's a total disaster because it loves to recrystallize while you're whipping it, making everything gritty. It's the perfect example of what we're trying to avoid.
Okay, so you've got your perfect syrup. Now the real fun begins. It's time to whip this stuff into a glorious, fluffy cloud. This part right here is pure physical transformation. The process is called aeration. All we're doing is taking a dense, liquid syrup and, using a whole lot of speed, forcing millions of tiny air bubbles into it, turning it into a light, airy foam.
And you can see the whole journey right here. First, you slowly stream that super hot syrup into your bloomed gelatin. Then, you crank that mixer up to high and let it go for like 7 to 15 minutes. And you just watch this incredible transformation. It goes from a clear, runny liquid to this thick, glossy, pure white foam that's literally tripled in volume. It's amazing.
But, things don't always go perfectly. So what happens when good mallows go bad? Let's troubleshoot some of the common mishaps.
It all comes down to whipping time. It is a super delicate balance. If you underwhip it, you end up with a gooey blob. It's a sticky, taffy-like mess that just never sets up right. Why? Not enough air got in there. But if you overwhip it, you get something that's dry and crumbly, almost like spackle. It's hard to spread and it's chalky when it sets. That's because you beat out too much moisture and it started to set in the bowl.
So to make sure you hit that perfect sweet spot, here's your checklist. These are the 5 things to look for. Has it tripled in volume? Check. Is it super glossy and white? Check. Does it hold a soft peak? Does it fall off the beater in slow, thick ribbons? And finally, does the outside of the mixing bowl feel just a little bit warm to the touch? If you can say yes to all of those, you're golden.
And look, this is exactly why a stand mixer is your best friend here. I mean, could you use a hand mixer? Sure, but standing there for 10, maybe 15 minutes straight, holding it on high speed, that's a workout. A stand mixer just gives you that consistent, powerful whipping you need to get perfect aeration without your arm falling off.
So when you boil it all down, the humble marshmallow is just a foam of sugar, water, and air. But by understanding the science behind it, the gelation, that critical temperature, the aeration, you've basically unlocked a fundamental secret of candy making. So it really makes you think, what else could we transform with this science?